say?
Yeah. I'm Keiji Ohnaka.
So in this talk, we take a tour down to the guts, right, in the immediate vicinity of an AGB star. This, I think, talk will show, among many other things, the promise of the PLTR as a tool for digging down inside.
Oh, okay. Thank you very much for the introduction. And for our next one, Institute for Radio Astronomy. And here are my collaborators, Peter Shell, who is the copper confluent. Right now, again, I'm Keiji Ohnaka from next one, Institute for Radio Astronomy. And here are my collaborators, Peter Shell and copper confluent, who are responsible for spectral imaging, which I'll show later, and then probably pilot. And I'm going to talk about the mid-arc-second imaging of comet dust clouds in the red giant nebulae with ESO's very large telescope interferometer. But first of all, a quick introduction about dust formation. And the dust formation is an important ingredient in the mass flow from cooled stars. Nevertheless, it is not understood very well yet. So, for example, we don't have a clear idea of where and what kind of dust forms and grow. And secondly, it is not entirely clear yet whether dust is the cause of the result of mass flux. But the recent high spatial resolution observations indicate this dust formation may be intrinsically clumpy. And this is a very good example of the famous copper star RC10-16. And these are the time series of diffraction-limited 2.2 micron imaging taken by a group from 1995 to 2001. And you can see several dust clouds and they evolve over several years. And our object, L2+, is a very nearby semi-regular M giant, and with an effective temperature of 2800 K and a luminosity of 5000 solar luminosity. So plotted on the AGF diagram is here, so the mass is estimated to be 0.5 solar mass. And it is characterized by unusually slow wind of 3 km per second. But the mass loss rate a few times 10 to the minus 7 kilometers per year. This is comparable to usual optical bright Mira stars. And probably the first evidence of dust clouds to this star was presented by Magallanes in all of 1986. They interpreted the time variation in polarization as due to rate growth and dispersion in an asymmetrical dust cloud. And Ion et al. Also find evidence of asymmetric brightness profile. Moreover, this object started a dimming event in 1995. So this panel, this shows the light curve in the visible taken from the AVSO light curve, the AVSO database from 1970 to the present. So what appears to be a lot of scatter, this is not a scatter or error, but it's just represent the pulsation with a period of 40 days. And in 1995, the star started to dim by 2.5 magnitude. And it's still ongoing. So this is interpreted as due to the episodic dust formation along the line of sight. And Jura et al. Took a mid-infrared image in 2001, so it was here when the star was still declining, and they spatially resolved the envelope. And this envelope is asymmetric or elongated in this direction. However, no one has ever imaged or directly saw the clumpy dust clouds which are supposed to be forming close to the star, because the angular diameter of the star is about 20 to 24 milliseconds. So in order to image the dust clouds close to the star, we have to have a milli-arc-second high angular resolution. And this is exactly what we can achieve at the very large telescope interferometer. So VLTI is a project to combine telescopes on this VLT side to form a big infrared interferometer to achieve spatial resolution much better than achievable with single-dish telescopes or even higher than ELT or TMT. And of course, these 8-meter telescopes are fixed, but on top of that, they have small so-called auxiliary telescope, 1.8 meter, and they are mobile, and you can see a number of the configuration, telescope configuration, depending on the object size and the scientific case, just like Ohnaka or VLA. And AMBER is one of the VLTI instruments working in the between the 1.3 and 2.4 micron. And with the currently offered maximum baseline and VLTI, we can go down to an angular resolution of 1 million per second. And the beauty of the AMBER is we can have a spectral resolution of 35, 1500, and 12,000. And after synthesis imaging is also possible. I don't think it's as straightforward as in radio technology, but it's possible if enough UV points are sampled. And this is exactly what I'm going to show in this talk. So we observed a deposits with AMBER between 2.2 and 2.35 micron. And on top of this AMBER observation, we carried out single-dish speckle interferometry observation with the Ohnaka instrument. The goal of this single-dish speckle interferometry observation is twofold. First, we can reconstruct the diffraction limited image with a resolution of 54 million arcseconds from this single-dish speckle interferometry data to see the global structure of the dust envelope. Second, and more importantly, we can carry out combined aperture synthesis imaging using the single-dish speckle interferometry data and the AMBER data. So in other words, we cover the very short baselines from 0 to 8 meters with a single-dish speckle interferometry and intermediate and longer baseline with AMBER. And this works as I show in a minute. So this is the UV coverage we got. So this central dot, big one is this is the number UV coverage, and these dots are the AMBER UV coverage. First, this is the diffraction limited image reconstructed from the number single-dish speckle data, and obviously the dust envelope is elongated in the east-west direction with a size of 300 times 150 milliarcseconds. And this direction of the elongation is not aligned with the mid-infrared image, which I showed a couple minutes ago. It was elongated like this. So, but that mid-infrared image was taken in 2001. So one possibility is the dust morphology has changed in the last 10 years, or the mid-infrared and near-infrared emission may originate from different regions. And to differentiate these two possibilities, we need the current mid-infrared image. And now we zoom in to this inner region. So this is the combined aperture synthesis image using Ohnaka speckle data and the AMBER data. And the image looks elongated or distorted because the beam is elongated like this. But we can recognize few dust clumpy structures. This one and this one, and there is something here. I will talk about this later. And then this very bright thing here. I think this is also the dust cloud in front of the star. And before going to the next image, I just want to mention these clumpy structures in the east-west direction. They just represent the extended components we saw in the speckle image. But the UV coverage in this direction is sparse. So there is something extended here, but the clumpiness of the image reconstruction in this direction is not very reliable. So we don't discuss these clumpy structures in the east-west direction. So in order to see the clumpy structures better, we decompose the image a little. So then you can see the clump structure, dust clumps here, there, and then there is something here as well. And this brown thing, this is the star. So it is clear this thing is probably the hot dust cloud in front of the star in the line of sight. By the way, the angular diameter of the star is about 24 milliseconds. So we have succeeded in imaging clumpy dust clouds for the first time for this red giant, which were only inferred from PLanetary and photometric observations. And we found dust clouds 20 or 30 milliseconds away from the star, which correspond to 2 splitter. radian away. And of course, these are the position projected onto the plane of the sky, and we don't know exactly where those clouds are along the line of sight. But we think the clouds are still close to the sun because they are quite bright in the infrared 2 microns, so they must be still quite close to the star. So the dust formation seems to occur at as close as 2 stellar radii, where the temperature is as high as 1700 K, and this temperature roughly corresponds to the condensation temperature of AO2 or 3 quantum grains. So the dust cloud we spatially resolve may consist of quantum grains. Secondly, the Norris et al. Recently found dust grains close to the star, again around 2 stellar radii and 3 minor stars. And they estimate the size of the grain to be 0.3 micron, and this may be the case for L2 And this grain size is important because this grain size, the grain of this size can drive the mass outflow by scattering on dust grains as recently proposed by Riviera 2008. And actually we can test this scenario by measuring the proper motion of dust clouds. If we adopt an expansion velocity of 3 km per second as measured by radio observation, then the dust clouds are supposed to travel 9 million arcseconds per year. And this is well resolved with VLTI Amber. And actually we have the second aim of VLTI Amber imaging run approved in 4 weeks. So if the run is successful, then we might be able to witness the initiation of the mass outflow in the normal red giants. So what do you think the ESO team who supported this beautiful Amber observation? And thank you for your attention.
Cool stuff. I see a hand in the back. Can we get a microphone to the back, please? Microphone to the back.
Just a question, the clouds you see, are they on your movie plane, or is this something, because you said you did something convolution.
Could you repeat again?
The clouds that you see are exactly inside your movie plane coverage.
Okay, so they are maybe IVAT because of this sparsely coverage. As I said, in the east-west direction, probably yes, but then in the north-south direction, probably no, because the visibility shows the evidence of small structures. I can show you the visibility. So this is the visibility plotted against the baseline length, and this thing is that this represents the extended component we see in the speckles image. And what remarkable is this one. This is the first lobe on the star, and this one is very high because if the star is just a uniform disk, then the second lobe should be as low as here. And to make this means this high visibility in the presence of some small scale structure.
So, I have a question.
Yes.
Scattering models the message and Blitzer 2011 shows that in the case of saturated scattering, the outflow speed should be about 18 to 20 kilometers a second.
Very fast. 18.
So I'm going to ask what we learned from the 3 kilometer per second outflow that you're observing.
I don't know. I don't know why this star has such a low outflow velocity. Unusually low.
Yeah, it's very low.
Yep.
Does anyone else? Well, we should save this for conversation. Repeat question.
May I comment on that? 3 kilometers per second. I think this made a couple of papers like in 1999 by Franz Engelstrom that low velocity outflows are probably indications of disk.
Okay, thank you very much. So since the coffee break, the speakers have been exploring incredible new technology